Hello, everyone. My name is Li Han-Ying, the president of Alberta AI Association. It's my honor to host this event. This event is organized by Alberta AI Association and CNKI. For people who don't know Alberta AI is founded by a group of volunteers related to AI and by to connecting the AI community, Alberta AI community to the world. And with that vision in mind, we organize this speaking series with the biggest digital publisher in China, CNKI. And our topic is new normal and opportunity of post-COVID-19 world. And we organized two series so far, and today's talk is the last lecture of series 2. Today's speaker is Professor Greg Kondrak. Professor Kondrak is a professor of University of Alberta and a fellow of Alberta Machine Intelligence Association. Greg's love of language drives his research, and especially his interest in the commonality across human languages. And his research ultimate goal is try to formulate a series of meaning or the ability to express the common concepts across all languages. And his work in 2018 on Voynich Manuscript was international recognized research story. And today, Professor Kondrak will walking us through how we can resolve the truly unresolved problem in the decipherment space. So please welcome Professor Kondrak to give his lecture.
Thank you. So this talk is about our work on unknown scripts, which was inspired by the famous Voynich Manuscript, which is a manuscript that was found about 100 years ago, and it has been dated by carbon dating to the beginning of the 15th century. There's only a single copy of it. It is written on animal skin, basically, and it is written in a script that is unknown, so there is no other sample of that script. And it's people have tried to decipher it since it was discovered about 100 years ago. So far, no attempts have been successful. Why we started working on it? Because when I attended a conference, a scientific conference in 2013, I saw a talk by Dr. Kevin Knight, who gave a presentation on this manuscript. And I was really fascinated by the mystery of the Voynich manuscript. And then I asked my student, Bradley Hauer, who's currently my PhD student, to work on this project, and this is a joint work with him. It was an adventure. Eventually, we published a journal article, and we presented that paper at ACL conference in Vancouver 3 years ago in 2017. It was, somehow, maybe a year later after that, the media learned about this project, and there was a lot of interest from the media over the period of maybe 2 weeks. Plenty of requests for interviews and explanation. I'm not used to dealing with the media. And what I learned is that you have to be very careful what you say, and that you have to be very careful how you explain your research, because the journalists don't really understand computer science, and they make up their own kind of interpretation, which is not really correct in most cases. So in our case, the media reported that we have deciphered the manuscript after 500 years of trying. This is incorrect. We have not deciphered the manuscript. Nobody has deciphered it yet. And then other media outlets follow that with even more outlandish claims that, for example, that we deciphered a manuscript which has alien characters, whatever that means. And other media outlets understood that alien means like UFO. So at some point, the press was reporting that we have cracked a UFO message from outer space. Fortunately, this has all died down. This all died down after about 2 weeks, and since then we have been able to work in peace on other projects. This project is closed. We don't really work on it anymore, but I think it's very interesting. So I would like to present it today in all its detail, in a scientific form, not like you know, kind of media form. And I understand that people here in the audience today can understand computer science and natural language processing. So let's start. So what is this all about? It's we are talking about deciphering a manuscript which is written in a script that is unknown. And in the world, many languages use their own scripts, including Chinese, of course. And most of those scripts are alphabetic scripts. So every sound stands approximately for one letter. But the way you express the sounds can differ. And in India, there are many different scripts that are specific to a language. And here we see an example of a script from a Sherlock Holmes short story about the so-called dancing man. So the dancing man is really a script where each different shape is a different symbol or different letter. And this is called a ciphertext. But the plain text is the actual message. In this case, the message is in English. And as you can see, the letter E, for example, is represented by the same letter in the script, the exception of the little flags that just mark the end of the words. So the decipherment task is to recover the original plaintext for a given ciphertext. Now, we make a few assumptions here, right? We make an assumption that we first are able to guess what language is the original message in this case, it's English. And the second assumption is we make an assumption about what kind of cipher it is, because there are many different types of ciphers. In this case, the cipher is called the monoalphabetic substitution cipher, which means that every letter is enciphered as a different symbol, but it's always the same symbol for a given letter. Right, so we're going to talk a little bit about how we define this task in order to perform experiments. And I'm going to talk about a new method that we proposed for solving substitution ciphers, which we later applied to the Voynich Manuscript, which is a text in unknown language and script. That involves finding out what could be the original plaintext language of the text, and also involved making assumptions about what kind of cipher it is. In particular, we made this assumption that it could be an anagram script, an anagram cipher, which makes it a very difficult cipher to decode. And finally, we apply these techniques to the Voynich Manuscript. So the main body of this work are the new methods that we show using scientific experiments, we showed these methods to work better than other methods that had been proposed previously for the same task. The application to the Voynich manuscript is kind of an interesting application, but it's not the main body of this work, right? So let's go to the task definition. In an alphabetic substitution cipher, as I said, each letter is mapped uniquely to one cipher symbol. As you can see here, this is done by using a key. On the left, we have the plain text, advise the mayor, so the language is English. On the bottom, we have the ciphertext, and the ciphertext produced from the plain text letter by letter by looking up each letter of the plain text using a key. And as you can see, this key, in this case, we have 26 letters of English, and each letter is mapped to a different cipher letter. These are uppercase letters in this case, but could be different symbols like dancing man or some other script. Right, so given the task is given a ciphertext like this one at the bottom, we want to find the plain text. We want to decipher the ciphertext. And we will assume that we know which language we're deciphering into, in this case, English. And we, in our experiments, we did tests where we generated many samples of the ciphertext synthetically, and then applied the program to decipher it, and we computed the accuracy of the decipherment, which was then compared to other programs that are available for this task. So first, I'll go through these previous work on this task, because our work was not the first on this task. The one that I particularly like is the paper by Ravi and Knight, which uses low-order character language models to find the optimal solution. And here we have a sample ciphertext. This is actually the first sentence from George Orwell's novel 1984, a famous novel. And this is the first sentence from this novel. Probably not many of you know what that sentence is, but I'll show the solution very soon. In the meantime, I'm showing you what this solver, or the program that implements this method, produces when it's given this ciphertext. As you can see, it doesn't make sense. It fails to decipher it. The text, the decipherment looks kind of English, but these are not actual English words, except maybe the word wind, which just accidentally happened to be generated here. So it is not the state of the art. Another paper, it was called a dictionary attack, which looks exactly at this, that when performing the decipherment, it specifically looks for the words in English. So it has a dictionary and looks up the dictionary to find out whether the decipherment produces words in English. And in fact, this decipherment produces only English words. All these words are English words, but put together, they don't make any sense. That's because this approach uses the so-called unigram word language model. So it only looks at a single word independently from the words that surround it. Here's another very good program by Norvig, a famous scientist, AI scientist. And this approach uses a character language model, but then uses a word language model to choose the best solution. It has this nice characteristic that it doesn't need to know where the words start and end. In this case, we do know where they start and end. And as you can see, the solver produces, again, a solution that is composed of English words, but together those words do not make sense. Finally, the work that was the state of the art when we started working on it was proposed by Nud et al. In 2013 at top-level conference, NLP conference ACL. And this one uses character language models, but they are very strong. They're up to 6 grams. So it's looking at sequences of 6 letters in sequence, and uses a powerful beam search to find the optimal solution. And the solution for this difficult ciphertext, difficult because it's quite short, again, is it produces English words, but it's not, we know that this sentence doesn't make sense because it doesn't use, in my opinion, the problem is it doesn't use a strong word language model. And that was our idea, to use both character language models and word language models to produce the best results. And here you can see what our solver produces. It breaks the cipher, and the plain text is actually, it was a bright, cold day in April. So a simple text using frequent English words, but it is very hard to decipher given that length of the cipher, which is short. The longer the ciphertext is, the easier it is to break, even if we just apply simple techniques like frequency analysis. Because as you know, every language has certain frequency signature for letters. For example, in English, the letter E is the most frequent. But not in this short text, right? In this short text, there is not a single E, letter E, so that frequency analysis would not work here. So how does our method work? It's composed of 3 stages. We first create a candidate key. So as I showed you, that key of 26 letters. We start from a kind of first guess, which is not very good, but then we modify that key iteratively to find a better key that produces better results. That is done by scoring the key. So we have the key, we apply the key to the ciphertext, and then we score the resulting decipherment. We basically compute how close it is to English, how similar it is to English using the word and character language models. And the third component is the tree search. So there's many possible keys to check. We cannot check all of them using brute force because there's too many possible keys, billions and billions of keys. So we have to do some kind of intelligent search for the best key. So I will now go and talk about some details of this method. The key mutation is basically given a certain guess at certain time of what the correct key is, come up with a better guess. So we generate new keys from the old key by slightly modifying that old key, and then we check whether they produce better results. And for this, we use the so-called pattern equivalence, which is basically looking at the signature of words. For example, will and jazz have the same signature, which is the first letter, second letter are different. The third letter is the same as the fourth letter, right? So we divide all words in English into these equivalence classes so that we know which words have the same pattern, and we have these patterns from the ciphertext. If a symbol is repeated in the ciphertext, then it produces a certain signature that will match only some of the English words. So we take advantage of that. Right, so I'll show this on a kind of a diagram. We have the ciphertext, just an example, a short part of the ciphertext, 2 words. We have the current key, which maps the symbol Z to letter E, symbol X to letter T, and so on. And that produces a given potential decipherment, which doesn't look like it's a real decipherment, but we want to score it in terms of how similar it is to English. So what we do is we find out the pattern or signature of this ciphertext word, 4-letter word, which the signature is that the first letter is the same as the fourth letter, but different from the other letters. And we come up with a word, hopefully a frequent word like that. That could be a guess, right? That we're guessing that this is the decipherment of that word in English. And from that leads us to modifying the key so that the new key, produces exactly this decipherment. And you can see that the new decipherment is much better, looks much better. So we will take this new key as our current guess and keep searching. The second component is key scoring, right? So now we have a key that creates a certain decipherment. The decipherment we want to look like English, and we use the language models to score it using unigram, bigram, and trigram models on the level of characters and words. So let's consider an example. These are two possible decipherments of our test cipher. As you remember, the plaintext is, it was a bright, cold day in April, right? And you can see that the second decipherment is much closer to the actual truth. For example, it deciphers the first word as it, but it's not completely correct. Now, if we want to find the correct decipherment, we want to be able to tell which decipherment, which keys produces a better decipherment. And in this case, we can apply the language models to score it, right? So we look at both possibilities. We look at the unigrams, bigrams, and trigrams of language models, both words and word language models. And this also we do with the character language models, where we look at sequences of 1, 2, and 3 letters. And this is very important because not all words will be in the dictionary. If a cipher has a word that is not in a dictionary, the word language model will not be able to identify it. But character language model is able to come up with a scoring of so-called out of vocabulary, OOV words. So after we combine these two different models, we come up with a score. It's a negative number, but the number that is bigger is the second one. And this allows us to choose this key, which is responsible for this decipherment, as a better one of the two. So we're going to use this key mutation and scoring in the search for the final key that should give us the true decipherment, right? And the tree is performed using the tree searching techniques, right? There is, the tree can be enormous, can grow exponentially, but we're going to limit the search by just looking at the best possibilities, best potential keys. So there are two search strategies. One is a beam search. These are the ones that we tried, and the other is Monte Carlo tree search. The beam search, it actually produces better results, as we found, but Monte Carlo tree search is also interesting. It's much faster and produces also good results, but not as good as the beam search. Right, so the summary of the method is to build a key tree through key mutation, assign values to keys with key scoring, and then search the tree with one of the search strategies, and at the end, return the top scoring key. Now, I will not go into details of the tree searching, because we don't have time for that. I'll now go directly to the experiments that we perform in order to validate our method, to compute how accurate it is, comparing to other available methods and the state of the art. So we took our training data by randomly sampling New York Times and creating synthetic ciphers. This is following the previous work. And these were our results. The results, sorry, these are the results of Ravi and Knight, 2008. Each paper pretty much publishes this kind of a graph. On the x-axis, we have the length of the cipher. On the y-axis, we have the percentage of error on the samples. So as you can see, for the ciphers of the length 64 characters, they only had 10% error rate, so 90% correct. However, for short ciphers, like say 8 characters, the error rate was almost 80%. So most of the attempts fail. What we want to do is we want to produce a method that produces a curve that is below this, right? So this is the state of the art when we published our paper, Nun et al. As you can see, it is better. It's hard to see on the very short cipher, which are extremely difficult because they may actually have multiple possible decipherments. But the best one to look at are these ranges of relatively short ciphers between 16 and 64 characters. And here, Nun's et al. Decipherment is better. The error rate on 32 letter ciphers is less than 10%, as opposed to 40% of Ravi and Knight. So how does our solver compare to that? Well, here's the graph of our results. As you can see, on the 32, 64, and longer than 32, the results are very similar. Both solvers are able to break these ciphers because they're long enough to find enough patterns. The big difference is on ciphers of the length of 8 and 16, where our error rate on the cipher of length 16 is only about 10%, as opposed to error rate of 60% of the previous state of the art. So this difference between blue and green here, this area, shows the improvement that we were able to achieve. Now, what can we also apply it to? We found some real ciphers in various books. For example, Goldbach cipher from the novel of Edgar Allan Poe. It's a 204-character cipher without spaces, and we were able to easily break that one. We also applied it to unsupervised transliteration between different scripts, different languages that use different scripts. And we also worked on so-called deniable encryption, so creating ciphertext that look like plain text. These are very interesting things. You can create a ciphertext potentially that you send, but if it's intercepted, people will just not see that as a ciphertext. They will think it's just a message, whereas in fact, it's a ciphertext that can be deciphered using a key. Okay, so far the summary. We have a new method of solving substitution ciphers. It works, it outperforms prior work, state-of-the-art results. So now, what about Voynich Manuscript? Can we apply these state-of-the-art techniques and possibly decipher Voynich manuscripts? That was an exciting motivation for us. So there are 3 problems. First, we need to decide what is the ciphertext language? What is the underlying language of the text? Second, we have to figure out what is the kind of a method of encipherment. Is it just a substitution cipher, or does it involve anagrams? And finally, apply it to the Voynich manuscript to see whether it produces some kind of reasonably looking text. So the Voynich manuscript here is shown on the right. It's composed of about 100 or 150 pages like this, handwritten, with many illustrations. There is very difficult. It's very difficult to get any kind of partial decipherment of it. There are some words written in the manuscript in Latin that made people think that this may be a form of Latin, but that doesn't really work very well. Some people said, well, let's look at those illustrations. These are plants. Maybe if we can identify the plant name should be maybe the first word in that text. So that would be something which is called a crib. So if we can decipher a part of the text, then that makes the decipherment of the whole thing much easier. However, none of those attempts have been successful. So can we perform the language identification? We came up with a new method of identifying a language. This is important also for actual unknown scripts that are historical scripts. They are not ciphers like Coptic, hieroglyphics or linear B, or Mayan glyphs that at some points were considered undecipherable. But they, in fact, were not ciphers, just different alphabets used for some languages that may have been, might have changed or even became extinct. So what is the problem? We have a ciphertext. We have samples of many languages. In our experiments, about 400 languages. And we build a classifier based on the samples, then apply it to the ciphertext, and it produces the best guess, right? It basically ranks the 400 languages according to their probability on this given ciphertext. There are three methods: character frequency, the simplest one, the pattern frequency that I mentioned before, and the trial decipherment. However, the decipherment is not necessary. Sometimes the decipherment fails, but in many cases we are still able to guess what the language of the plaintext is. So we look at, for the letter frequency, we look at the distribution of symbols in the sample and compare it to the actual distributions from actual languages. That's one method. If we use this method, we can just compare these distributions to different languages and find the best match using a special kind of formula for finding the match between two distributions. Okay, so in this case, in this example, the output would be Spanish because the distance between the Spanish distribution, sorted distribution of symbols and the ciphertext is the smallest. The second method looks at the patterns, which I mentioned before. This pattern of the word seems says that there are two letters E, two letters S, two letters M. Even if we cannot decipher these letters, if it's a substitution cipher, the distributions of symbols will match that pattern. And the composition patterns work pretty well, better than just simple symbol letter frequency. And the final method, which actually works the best, is so-called trial decipherment. So basically, try to decipher a ciphertext into any language, and then score the resulting decipherment using the methods that I mentioned before, and pick the language that gives us the highest score. So for example, given this ciphertext on the top, this is our decipherment. In this case, we are able to decipher it perfectly into English, and of course, that will give us a higher score. But even if that decipherment is not perfect, it should still give us a higher score for English than Italian. Okay, so in the interest of time, I will not go into this details of the algorithm, but we also created an algorithm that we thought would be working very well for this problem, and will be fast enough to try many possibilities. Okay, so how well does this work, right? We conduct experiments on language identification using a text that is available in many languages, Universal Declaration of Human Rights, in 380 languages. And then using those samples, about 1,000 words each, we choose the ciphertext language. We try to guess the ciphertext language. We compare to previous work of Jaskiewicz, 2011. So here are the results. The previous work achieved on the samples about 48% accuracy. Our character frequency method, which is similar to previous work, achieved 68%. The decomposition pattern achieved 85%. And the trial decipherment achieved up to 97% accuracy in our tests. So we were quite confident that this method is able to find the language of the ciphertext, provided that that language is among the samples, in our case, 380 languages. If we don't have a sample of that language in our samples, then the program cannot find that language. Okay, so another thing that is interesting that we investigated is anagramming. We noticed, actually, we were not the first to notice that the words in Voynich Manuscript seem to follow certain order, and that gave us idea that there may be some anagramming going on in the encipherment. That would make the problem more difficult, but it turns out that we can relatively easily deal with anagramming. We have developed methods to deal with anagramming so that we can still decipher the text. So our assumption is that this is one-to-one substitution cipher with anagramming. If there is no anagramming, that method will still work, because if you don't do any anagramming, then the letters are still in some sequence. And what our approach is to first reverse the substitution after identifying the language, of course, and then they reverse the anagramming, and that produces the plain text. Can it work? Well, it turns out that it works pretty well, right? In this case, we have the ciphertext at the top. We decipher the letters. That doesn't produce an English text. But after rearranging the letter, like this, for example, THIS, after rearranging the letters, we obtain the actual English plain text. Right, so again, how do we do the anagramming? It is a simple technique, statistical techniques based on hidden Markov models, where we have sequences of emissions and states. The states are words, the emissions are scrambled letters of those words. So for example, here we have some letters. You can see that for us it's very difficult to actually find out what is this letter, what are these letters, what word it represents. But for a program, it is actually not difficult, because every sequence of anagram letters can be divided into these equivalence classes of words that can be then recovered by the program. Right, so as you can see here, that these words are actually, there are 3 scaly serpents, right? And even though for us it's very difficult to guess that, our program is extremely efficient at that decoding. Okay, so going to the final experiment, we tested all these different modules together, and our accuracy was very good. It was on average above 90%, using samples from 5 different languages. So we were quite happy with that, and we were ready to apply it to the Voynich manuscript. So let's see what happens when we apply all these powerful algorithms to the Voynich manuscript. First question, what is the language of the Voynich manuscript? Well, we used our set of 380 languages and apply it to the Voynich manuscript. What do you think the results was, right? So here are the results. This is the closest to this y-axis, the more likely this is the language. And this is binned by the distance. So there are 380 little squares here. And as you can see, the Hebrew surprisingly showed as extremely close to the Voynich manuscript. Definitely the best guess. If the language of the Voynich manuscript is among those 380 languages, then Hebrew is the best guess, and we can be confident about that with about 97% confidence. But we are not sure if the language that is used in Voynich manuscript is among those 380 languages, or it may be actually not any human language. Maybe it's really an alien language from UFO. So what happens if we try to decipher the manuscript using our powerful decipherment program? So we applied it to 10 pages from the manuscript, and we tried to decipher it into those 5 languages: English, Italian, Latin, Hebrew, and Arabic. These are plausible languages that could be used in 15th century for enciphering the text. So we found that Hebrew again gave us the best results. This is the percent of words that we were able to obtain from the manuscript. Put together, those words do not produce any kind of reasonable sequence that can be interpreted, but there is still many words from that language that can be found. And that's true of any language. The decipherment will find letters from any language, but for Hebrew, it finds many more languages. So in conclusion, we have proposed a new substitution cipher solver which outperforms previously published solvers. We can extend that solver to handle anagramming, and we can accurately identify cipher language with 97% accuracy. When applied to Voynich manuscript, it points out to Hebrew as the most likely language from the languages that we can actually test. In addition, it produces it identifies many Hebrew words in the manuscript, although it is not clear whether these are actually correct decipherments. And some of these words are related to the topics that are suggested in the Voynich manuscript by the illustration in the manuscript. Okay, so that's all. Thank you.
Okay, thank you, Professor Kondrak. It's excellent lecture. I don't have many knowledge about this space, but after your lecture, I know the space about. And it's quite dark in Edmonton, so probably allow Professor Kondrak turn on the light. And it's a kind of a mystery, like when Professor Kondrak give the lecture, it's kind of mystery, like it's become dark, and now we kind of be bright, and we resolve the mystery.
Well, that corresponds to the Voynich manuscript, which is still unsolved. It's still a mystery.
Yeah, it's very well, like lightning control. Yeah. And I have quite a few questions from the audience. And so the first one, it's like in Wikipedia, I check out the Wikipedia, and Wikipedia, there's an article about the Voynich decipherment manuscript, and it listing out all the research in the sequence, and Professor Kondrak's research is listing there, and that's a big achievement. But after that, there's more research down the road. So what's the new research down the road people dealing with this problem?
Yes, so this problem continues to fascinate many people from different kind of disciplines, and there's every maybe few weeks or that often, there is a new attempt, and there's a new media report that the Voynich manuscript has been deciphered. But unfortunately, every time you look closer at those decipherments, they don't stand scrutiny, right? So typically there is only a short part of the manuscript that is deciphered, and the rest of the decipherment is kind of left as a future work. So unfortunately, I don't think that it has been achieved, but it could be achieved in the future. Definitely, I don't think, some people say that there is nothing to decipher, that it's all a hoax, that somebody created a joke, just to make a joke, created this very expensive manuscript, which I think is unlikely that somebody would put so much money, because it was very costly 500 years ago to create a book like that, just to deceive people. I really think that there is some cipher, there's some message in that text.
Okay. And in the Wikipedia article, like after your research, and people are challenging like the accuracy, you declare, it's not necessarily true. How people can make such kind of judgment, or some Hebrew language expert saying it's not deciphered yet. So what's the criteria to make such kind of judgment?
Yeah, a lot of this misunderstanding is because people thought that, based on the media reports, that we claim to have deciphered this manuscript. We have not deciphered it. So we cannot. That is not in the paper. We publish a journal paper, and anybody can look at it, and there is no claim of decipherment. We only applied it just to apply to a single sentence, to show that if you take a very short part of the manuscript, it's not unlikely to produce a reasonably looking decipherment. The problem is that you cannot extend it. You cannot just decipher one sentence and claim that you have deciphered the manuscript. You have to decipher the whole thing. And regarding the Hebrew claim, this is also a misunderstanding. We are not claiming that this is Hebrew. We are claiming that Hebrew is the most likely language, if it is written in a natural language, and if that language is among the 400 languages that we have tested, then Hebrew is the most likely language, and that we definitely have evidence to prove that in the form of our experiments in the paper. It's all in the paper.
Okay. And so can people using your tool to decipher the whole book, and then the Hebrew language expert can have more meaningful, like the whole book decipher?
No, we don't know any Hebrew, so we couldn't even, like, we applied the program to the manuscript, and we got the Hebrew looking text, and we had no idea what it means. So we asked some people that speak Hebrew, and they told us, no, it doesn't look like any text. It's just gibberish, right?
Okay.
Yeah, as I said, we have not deciphered this manuscript, so there's no such claim that we would be making.
Okay. So, but it's still possible, after further research, it's possible, decipher this book in future.
I believe so. I don't have evidence for that. We published a paper where we made some claims, and we provided evidence for those claims, but we don't have the evidence that this is actual text, and we have not deciphered it, because that would be the ultimate proof. If you can decipher it, then it is written in human language, right? Otherwise, some people make these arguments, well, if you analyze some statistical properties of the words, the chapters, then you can argue that this looks like a human language. But of course, this is just an argument. It's not evidence.
So what's the further work need to be done on like to decipher this book? What's the further work? Because in your example, like if some simple English cipher text, then like we can decipher it, and then we know like the plain English, and it's kind of totally deciphered. So for this problem, when we can reach that stage, and what kind of research need to be further done?
Yes, so personally, I found this very interesting to work on the Voynich manuscript as a motivation, right? So we had this as a motivation, but then we did, I think, good science, and we produced we focused on a specific task that also other people did, which is decipherment. And we applied the modern NLP techniques to that problem, and we achieved state-of-the-art results. So we learned a lot in this project. So even though we did not decipher the manuscript, I think it was a very interesting and learning experience for us to do this. And I think that should be also the case for other people. You try to decipher it, and then you find out that you have to learn more about the modern techniques. And then these techniques that you develop find also sometimes applications that you did not think about. For example, one of the applications was unsupervised transliteration between languages that use different scripts, like, say, Russian and Arabic, right? And so that's one possible application. And our paper has been cited in some publications from physics, right, which we would never suspect. But these concepts that we developed are also applicable in other areas.
Yeah, I think that's a very good point. Like this kind of research, it's a good research motivation and developing the technique for practical uses.
That's right.
Yeah, okay. And related to this question, I have a question from the audience. And the question is, the Voynich manuscript cover the content of herbals and herbals, medicines, biology, cosmology, and astronomy subject. So the question is, which subject are you interested in more, like for different like subject in language or in this manuscript?
Yeah, so that's very interesting. Voynich manuscript is such a thing that people from different disciplines find something interesting in them. For example, biologists or botanists look at those illustrations of plants. People that know Latin very well, they try to decipher into Latin. People that know history of the Jewish people came up with a hypothesis that it looks like something that Jewish people would do in the 15th century, and so on. So everybody provides their own expertise on the topic, and that is part of why this manuscript is very interesting. Our own approach was, we are computer scientists, we work with natural language, and that's what we focused on. We did not deal with the illustrations because we are not botanists. We did not deal with the pictures of people because we're not historians. What we did is we focused on the decipherment, and this is the subject that we know very well. And we tried to see how much that could help in deciphering that mysterious manuscript.
Okay. Yeah. So the next question is, when you use the pattern equivalent model, there seems to miss something that the same capital in the ciphertext may also represent the same capital in the decipher text, or there's also a possibility that the same capital may share several other capitals, such as ciphertext. However, to represent ABCD in deciphertext. So I'm not sure what's the question about, but
yeah, so the thing is, like we are, as I said, computer scientists, and we are used to working with noise, right? That means not everything is perfect, right? Sometimes, even if you make a typo, right, then you will not find that word in a dictionary. But the algorithm that what we developed is quite resistant to noise, thanks in part to those character language models, which do not depend on the actual word being deciphered, rather on sequences of letters that are mostly preserved, definitely over 90% in the text. So that's why I believe that our approach is quite robust with respect to noise.
Okay. And the next question is, in this research requires expert on like ancient herbal language or medical history or a cryptograph. So do you have a plan to organize so many professionals to tackle, like move forward this research? You kind of answered this question a bit already.
Yeah, actually, there were some conferences on Voynich Manuscript itself, but I don't think we need to put people together, especially nowadays, to work together. We can, as scientists, we work together in a sense by reading each other's papers and building on the work of others. So it is a kind of a joint effort, but it doesn't actually involve direct communication.
Okay. And the next question is a little bit general question here. Like when you show the example of decipherment, you mentioned your method use guess the original cipher. And in this case, like for your guess, what's your your reference for your guess?
Oh, for the initial guess we used frequency, letter frequency. So in English, for example, the most frequent letter is E. So if we were deciphering the text into English, we would look for the most frequent symbol and guess that it's E. And then the second most frequent symbol is T, so we would do the T. Of course, that's just that doesn't really work perfectly, but it's a reasonable guess to start with. And then we would use the tree search to improve on that guess.
Okay. And for the decipher text and without knowing the original text, so how, like it's an unsupervised problem, how like you can make some kind of criteria saying this is the original text, because we don't know the original text.
Yeah, so we did that separately for all 400 languages. We would take one language, say Spanish, and say, okay, we'll try to decipher this into Spanish, and then make a initial guess based on the Spanish frequency, and then try to get as good as possible the Spanish decipherment. And we repeated this for all languages. So that was quite a bit of computation. It took some time, but we were able to complete it for this experiment on 400 languages. And that's why we are confident that the language that is most likely, the most similar is Hebrew among those languages.
Okay, and so for like this decipher approach in your research, like can this used for the military purpose? Like it's the example you showed to us looks like it's quite like simple, not very strong cipher. But if we like encounter some very strong cipher, like the military level of cipher, like this kind of tool will like make the military cipher becomes impossible anymore.
Yes. So actually, this is a very interesting area. I actually teach a course on cryptography, and we discuss these historical ciphers, military ciphers, especially in the Second World War. There was a cipher war between the Allies and the Axis powers, which Alan Turing, the famous Alan Turing, was involved in that. And he was responsible for breaking the famous Enigma machine cipher, a very strong military cipher that actually inspired him to build the first computer. In 1943, I think he built something like a computer in order to break those ciphers. So, so it's definitely a very interesting area. And but what we realized after working on this is that much of it is mystery, because the governments don't like to tell anybody about their own methods of decipherment. So we only find out after 50 or 60 years what actually happened. So I'm sure right now there are special departments. Many countries have their own special decipherment departments that work on those computerized decipherment methods and are very good at it. But the difference with us is that we have nothing to hide. We do this project and we make it available for everybody to use. And that's because we are scientists. We are not the government military experts.
So for the example you show and the military level of cipher, so what's the difference? It seems to me it's the same. It's just a cipher differently, and how it's cipher, it doesn't matter for decipher. I can so I try to understand what's the difference here.
Sorry, but the difference between what?
The difference between the simple ciphered example you show in your example, and the military level of cipher text. So what's the difference, the difficulty level difference, or decipher differently? So what's the difference like?
Yeah, well, so, another thing that we all use ciphers, when you pay for something on the internet with your credit card, that transaction is enciphered, right? So these are known algorithms, for example, the RSA algorithm, that are based on, their safety is based on very large prime numbers that cannot be factored. So these are mathematically proven techniques that create ciphers that are safe, right? So these ciphers, they are guaranteed, they're proven that you cannot break them, right? A simple cipher like a substitution cipher that people could use back in 15th century was only simple ciphers. That's why our assumption was that the Voynich manuscript isn't ciphered using a simple technique, because back then people didn't know these advanced techniques that we know now.
Oh, okay. I kind of understanding this technique maybe be able to decipher for simple ciphered text. It's not for RSA kind of ciphered.
No, definitely not. No.
Okay.
Actually, nobody can do that.
Oh yeah, for sure. Yeah. Otherwise, it's a fairly significant thing. Yeah. Okay. Yeah. I have quite a lot of questions from myself, but because of the time, and we will ending the event now. But I will have a chance to ask Greg in person. I'm lucky I'm in Edmonton. For the people who have further questions, you can definitely search Professor Greg Kondrak's name, and you can find his personal page and be able to reach out if you want to ask further questions or have some discussion collaboration. So thank you, Professor Kondrak, to devote his valuable time with us and share his insight and knowledge with us today. So our event will close now. Have a nice evening or nice day today.
Thank you.
Thank you. Bye-bye.
Bye-bye.